Thank you. Well, good morning, everyone. Thanks for showing up. I was going to say thanks to Neil for setting up all the hard bits of what heat pumps are and all the rest of it. So hopefully this doesn't land on you too fresh. I am the Group Sustainable Development Director for Star Refrigeration. We are an industrial refrigeration company dating back to 1970. So more common ground for us would be fish fingers, ice rinks, data centres, food factories of other types, distribution centres. To give you a feel for the scale of things, we look after all of the Tesco and Asda logistics centres in the UK. So if you're as fond of frozen chips as I am, then we're looking after you in some shape or fashion. I'm also, this is my second year, I'm a visiting professor at Edinburgh Napier University, and that's a great opportunity for me to formalise what I've certainly been involved in the past, which is a little bit of knowledge sharing and getting involved with students. And actually, dates, I'm going to make Mark feel old now, but all the way back to 2014, Mark and I first met, and he helped with a couple of students at Glasgow University, where we used the IES software to model the entire campus. A couple of really clever guys were doing that and did a brilliant project showing how you could heat an entire university with heat from a river. This story hasn't changed any. This is very much about how you tackle large buildings. Neil will give us, I'm certain, a really good insight into medium-sized buildings and smaller buildings. I'm a fan of that as well. It's the right recipe in the right place as far as I'm concerned. I have a ground source heat pump through the door behind me, and that's been keeping our family warm for 4 or 5 years now, with not any sort of hint of any trouble. So you would have to be living under a rock not to have picked up about climate change, and the single largest contributing factor to that is the release of carbon dioxide into the atmosphere. There are other things that cause problems, such as methane and some of the working fluids used in refrigeration and heat pumps. The single largest reason for carbon dioxide being emitted is burning fossil fuels. And one of the two largest reasons for burning fossil fuels that certainly are holding fairly steady are for transport and also for heating. Burning fossil fuels for generating electricity is dropping year by year. It's got a long way to go, but it's definitely on the decline. Transport, I'm not going to talk to you about, but how to heat buildings without burning methane is the topic of today. So definitely a threat that we have to try and take. But equally, there's an opportunity. The pandemic that is slowly receding into the past is an interesting starting point or benchmark. I'm sure there's some interesting studies going on about everything that happened during that. But one of the interesting things for me was air quality, and how much air quality improved during the piece. There's somebody not on mute. If you just go on mute, please, Matthew, thanks. Air quality improved dramatically, but not much more than about 40% better. And that's simply because we were still using fossil fuels for heating buildings. So the opportunity here is to do something better than what we've been doing. So heat pumps and very simple thermodynamics. We are harnessing a vapor compression cycle. Those less techy in the room, we compress a working fluid at line number 1 here. We then extract heat from that, and we deliver the heat through line number 2, and then we expand the working fluid back through 3 and 4. And the trick is to get as much heat out as possible for the minimum amount of work possible as well. There's a few folk not on mute. Could you just jump onto mute, please, Melissa? Thanks.
Work out how to. Computer's doing something funny. Hang on, sorry, bear with me.
So the thermodynamic cycle, this is not new stuff. It was dating away back to 1852. Lord Kelvin was talking about this. And so we have done some very big heat pumps, and I'll show you a short video just now, just to give the context of what I mean by a heat pump. So this is at Queen's Quay down in Clydebank. That's the energy centre on the left. We're looking up the River Clyde towards Glasgow. That's West College with the checkered fascia there. And inside, these are the heat pumps that we manufactured in our factory in Glasgow, utilising a variety of components that we've sourced from expert suppliers mainly around Europe. So that is what I'm going to talk about today, which is a big heat pump, not the sort of thing that might sit outside your back door. And there's a better photo. It's quite hard to get a decent photo because they're so big and fill the room. It's been very successful. It won Heat Pump City of the Year in 2021, I think it was. And really, the reason that the local authority decided to do it, this graphic stolen from the European Heat Pump Association, but there are a variety of reasons to think about doing something different. I like to think about the future in terms of what the destination looks like. So we certainly are thinking about clean air that I've mentioned already. We're certainly thinking about renewable energy, and we're certainly thinking about energy efficiency. Supply security, for sure, that is still very much on the news every night. Less obvious would be smart grids and what that means. We're basically moving our system forwards from 60 centralized power stations to 60,000 dispersed power stations or wind turbines, as the case may be. And that creates all sorts of challenges in the energy supply because they are not nearly as unsteady as the more traditional devices. And so what we have to do is flex our demand. So if we have a variety of electrical devices that we can ramp up and down depending on the amount of generated power, that's going to help us. And then, of course, not unrelated to supply security, but less imports. The UK, when I last looked at the data, and this is going back a good few years, it was about 40 billion pounds of fossil fuel consumption, of which 50% was imported. That is not the basis of an economy which is starting at zero. It's starting at a negative position because we're effectively having to export our cash to get these fossil fuels in. The values are probably up at least 25% from that position now. So if we can do something much more local, that will be much better from a macroeconomic perspective. So more of it, and what's the problem? Well, the problem is that society is very complicated. We've got a variety of different types of buildings, from a classic bungalow that you might see in Edinburgh, Glasgow, typically dating the 1950s, to brand new houses, to new areas of cities, to the older bits of cities that are continually being built out, to the very traditional tenement houses, very common in Glasgow, and of course industry as well. So there's at least 6 different places that we're burning fossil fuels to try and heat the buildings. And then of course there's the other aspects of it as well. There's a sort of middle-aged, if you like. I don't mean knights and so on, but 1980s onwards, let's say, properties, probably pretty well insulated in some respects, but definitely heated with fossil fuels and gas boilers. And then just to throw another layer onto this, who owns what? And social housing brings a variety of different ages of property, and also that ownership piece is very, very much different to be trying to deploy a solution in that case than an individual house that's owned by a private individual. So what we're certainly going to have to do is find a solution for all of these. So to take the very specific thing, and when I'm talking about heating, the segment I'm thinking of is this bit. If I can just go back one slide, this bit here, which is older bits of cities and maybe high density bits of cities, and any new bits that are being built in the city centre. That's the segments that I'm thinking of. I'm not thinking of brand new houses or the more traditional standalone pieces. And we are of course interested in industrial applications, the type of business that we are. That's not what today's session is about. It's about the chunky bits of cities. So looking at Glasgow city centre, how much heat do we actually need in Glasgow city centre? So there's a very good freely available map in Scotland, which is the Scottish Government heat map, and every little dot represents a quantity of energy requirement or heat requirement. You can draw a blue line around that and it gives you a number. So the demand that we've got in the centre of Glasgow, Central Business District, we might call it, is 730 gigawatt hours per year. That's a very, very large number. So how are we going to do that? So what we used was some thinking which we've badged under Heat Vision 2030. Apologies for the spelling mistake there. Vision, VISION 2030.com, and that basically said, let's work out what this might look like. And so the 730 gigawatt hours per annum, a single energy from waste plant, which is a very typical way of doing traditional district heating in Denmark, for example. There's one being built near Glasgow at the moment, and there is about 12 megawatts of thermal heat available at ready-to-use temperatures. And we can just, therefore, put that heat into a network of pipes and take it to the city centre, and the job's done. Unfortunately, life's not that simple. That would only give us 96 gigawatt hours per annum versus our 730. So you would need significantly more than just one plant. And actually, there is a Scottish Government phase down of these sort of facilities. I don't think there will be any new planning consents granted. There are a few not built yet with planning consents, but the point being, there isn't likely to be enough trash anyway to heat all our cities. Paul Younger, who was at Glasgow University, once observed that you need the waste from 10 cities to heat one city. So if that's your plan, you're going to score fairly low down the percentage scale. We need something more than just finding trash and burning it. So what about the river that runs through the centre of Glasgow? So another government website, this is the National River Archive. Every single river in the UK, you can find a monitoring station upstream of the tidal weir and get a flow rate. And in the case of the River Clyde, 95% of the time the flow rate is 9.689 cubic meters per second, or 9,689 litres per second or higher. And so that is this line round about here. And of course, we want more heat in the winter time when it tends to be wetter. So actually, the rivers are fuller than that. This is a logarithmic scale. So if you'd done your maths on 20 rather than 10, it would still be plenty wetter than that all the time. So what does that mean? The river flow rate, there we go. Take it all down. If we cooled it by 3 Kelvin, which the Environment Agency are happy to do, that would be 139 megawatts extracted. The heat available from the heat pumps, because of course they consume some electricity as well, roughly in a ratio of about 3 units of heat for 1 unit of electricity, would be over 200 megawatts available. So that's 4.2 times as much as the city centre needs. So what does this all mean in terms of what the heat pump system might look like? Just to go back to the science of it, the physics, you have to have a source of heat, that's something that you can cool down. So that might be the air, it might be the ground, it might be rivers, it might be water that's underground. You have electricity coming from somewhere, and you have the heating system. If you can do a good job of working out what each of these are, you've maybe got a project. So looking at them in turn, the electricity that we need, we definitely need a big supply of electricity for big heat pumps. That's just stating the obvious. We want it to be predictable and local. We don't want to be importing it. We want it to be, we need to be able to predict when it's available so that we can make sure we are running like that. And of course, super expensive electricity is going to mean super expensive heat from heat pumps, and that's not going to float people's boat. In terms of on the right hand side, I've blanked out the modern houses. I don't see that necessarily as the right route, although if the pipes were running past a site, that isn't out of the question to do it that way. So it is these 3 areas of the city, and then the electricity piece. Sorry, I was getting confused there, mixing up the two. But the electricity, we're looking for something that's clean and cheap. The heat source is what we want to be predictable. We don't want something that is you go looking for it and you can't find it. We want it to be predictable in that sense. So take all these things together. What does a heat pump look like? Well, heat source you have to have the technology to work. You have to have the heat demand. And if you get all that in the right components, you get a return on investment, which makes the thing economically viable. And then the investment funds will come in, and these will be significant capital projects, measured in probably billions of pounds around the country. So it's quite clear it's going to have to be a big solution. What gave us the confidence to do this? Well, we had done it before over in Norway. Way back in 2010, we built this heat pump in an energy centre in Drammen in Norway, and that's now been running well over 8 years. It's up at about 12 years now, and it's the primary source of heat for this entire city. So we know that the fjord is going to be there tomorrow. We know they've got a supply of electricity. They've got the heat pumps. They're in the conversion business of converting electricity into multiple units of heat. It took us a while to get that going in the UK, despite the fact the UK government were subsidising this type of activity in the order of about twice the cost of burning gas projects would receive in the renewable heat incentive. And so we thought this was going to be significantly easier, and it was. It wasn't until the local authority, Western Bartonshire, appointed Vital Energy to design the sorry, Darren, can you go on mute, please? Thanks. It wasn't until the project was really taken forwards. We are not at the top of the tree in this. We're you could call us a tier 2 contractor. We're just an equipment supplier. So we needed to get people interested in doing this, and it's been very successful. They just need to get more buildings connected onto this. But any building that connects now, and this is a really interesting proposition for any of the buildings in Clydebank, any building that connects now is probably going to reduce their carbon footprint by about 90% by that single activity of connecting to a heat pump. And that's a really simple way for these buildings to do it. And of course, the facility, when heat pumps are running, is zero local NOx that I mentioned earlier. So air quality is a big piece. So there's the heat pumps when they're being delivered. One of the Titan cranes just in the background there. The bit I want to draw your attention to is this rather boring looking cylinder here. This is the thermal store. To put it in context, and the camera does lie in this case, that's a 2-meter high door. The thermal store is more like 8 meters high. But what I see this thermal store as is this is a bit of a time machine. And because what they're able to do is buy electricity at one time of day and deliver heat at a different time of day. There doesn't have to be that direct connection. This big hot water bottle, if you like, you can heat up and then release the heat later on. And that lets us play some tunes with the supply of electricity. And predominantly the major reason for doing that is the cost of electricity. Gas, which is a fixed price during the day, during the year, does vary with year to year, but electricity is varying on a half-hourly basis. So there are 48 different prices of electricity in any one day. They will be different yesterday than they will be tomorrow. And so playing tunes with that is definitely to the advantage of the operator. Harnessing these heat pumps, here they were in our factory just before dispatch. It gives you a slightly easier view, but basically it's about this electric motor at this end is the key thing. So as I said, one heat pump city of the year. So we did manage to repeat this. This is down in Bristol during construction. This is another 3 megawatt heat pump taking heat out of the floating harbour in Bristol. And they too have set this up. In terms of the economic impact of that, this is part of a cluster of assets that have now been bought by some institutional investors. And their job is to roll this out across the city and create an even bigger network, and that's there's a lot of activity down there. So again, any building connecting to this district heating, effectively it's job done in terms of decarbonising heat, which for very large buildings is very difficult to do. And that too won Heat Pump City of the Year. So twice in a row, that has been the winning ticket. Very quick comment about the working fluids. You would have to be living in a cave not to have heard of CFCs, and they were invented in round about 1920 because it was decided that things like carbon dioxide, which had been used, and ammonia, which had been used, were a little bit too tricky. CFCs were invented by some very clever chemists, and that was fabulous all the way up until about 1985 or so. And then the ozone layer was seen to be being damaged by this, and they were phased down. And it's actually the only of 8 United Nations indicators where we're moving in the right direction. Every other UN indicator that our sustainability index is moving in the wrong direction. So things like air quality or water quality and so on are all going backwards. The repair of the ozone layer is definitely creditworthy. We replaced them with other synthetic chemicals, and then they were phased down. There's now another phase down on HFCs, and we'll see where that takes us with some of the more modern HFOs. Draw your attention to ammonia there. It's the only arrow that goes right from back in the early days, the late 1800s, all the way to the present day. And there are other natural working fluids, carbon dioxide being one, hydrocarbons being others. That's not to say that they are created naturally, that they will be coming from a chemical process, but they exist in the environment naturally. And that's a really key thing, is that if there's any small amount of leakage, that is not creating the same damage. HFCs, for example, the reason they're being phased down is they're 1,430 times as potent as carbon dioxide. So if they leak from any system, that's going to be incredibly damaging. So let's try and do less of that. So going back to the river piece and why this is significant, this was a map done by DEC way back in about 2015 or so. And it basically plotted the coincidence of heat demands shown in orange and red and rivers. And actually the bit that it didn't really talk about was the coastal and the estuarine aspect, which is the bit that we've been typically harnessing. And so you can see that, broadly speaking, wherever there's a demand for heat, there is a river. And that's principally historically because that's where our ancestors built their cities, their towns, then cities, because they wanted access to water for all sorts of reasons. And so the key thing in all of this is it's about the predictability of this. We know exactly where the rivers are. They're still going to be there tomorrow. Really, the bit that's unpredictable, if you like, is the price of electricity. And the proposition here is that we need to harness electricity at a much better cost. So I think, Mark, and the benefits of time, I'll probably leave it at that, other than just to make the reminder again, the Heat Vision 2030 lays out a lot of this case study piece. And I'll pass over to Neil if he has been able to join us.
That's brilliant, Dave. Yeah, I think we managed to get Neil to jump on his phone for sort of voice now. So hopefully, Neil, we can hear you now.
Yep, can you hear me?
Yeah, perfect.